Hello everyone! In this probability statistics in Python tutorial, we explain how to model the binomial distribution in Python by using the SciPy library and the statistical function module called stats. In particular, in this tutorial, we explain number 1, how to create a binomial distribution in Python. Number 2, how to create a probability mass function of the binomial distribution in Python. Number 3, how to compute the moments of the binomial distribution. Number 4, how to generate a plot of the probability mass function of the binomial distribution in Python. And number 5, how to compute the percentiles of the binomial distribution in Python. Among a number of useful things that you will learn in this video tutorial, by the end of this statistics tutorial you will be able to generate a graph of the probability mass function of the binomial distribution. The graph is shown over here. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this video tutorial, as well as more than 450 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start with explanations. First, we will provide a brief summary of the binomial distribution. The binomial distribution is a very important statistical distribution. For example, this distribution is used to model the process of tossing a coin n number of times. In every random experiment of tossing a coin, there is a probability of p of obtaining the head and the probability of 1 minus p of obtaining the tail. If the coin is fair, then the probability of two outcomes is equal, and p is equal to 0.5. The binomial distribution provides us with the probability of obtaining k heads in n number of trials. For example, it can provide us with an answer to the following problem. Suppose that a fair coin is tossed 10 times. What is the probability of obtaining 3 heads? For example, the random experiments can look like this. Experiment 1. Head, head, tail, tail, head, tail, head, tail, head, tail. Experiment 2 can look like this. Experiment 3 can look like this. In every experiment, we toss a fair coin 10 times. To answer this and similar types of questions, we need to mathematically describe the binomial distribution. Let us formally define the binomial distribution and its probability mass function. We are considering a random experiment where there are two outcomes called success and failure. In a single experiment, the probability of success is p and the probability of failure is 1 minus p. We are performing a random experiment n consecutive times. Formally speaking, the binomial distribution is mathematically described by the probability mass function given over here. Let's explain this important equation. In this equation, n is the total number of random independent experiments that are also called random trials. P is the probability of success in a single experiment. K is the total number of successes in n independent experiments or random trials. And this notation, P, when capital X is equal to K, is the probability of obtaining K successes in n independent experiments. Finally, this notation is the binomial coefficient. The binomial coefficient is often pronounced as n choose k. After we summarize the binomial distribution, it's time to start with Python implementation. The first step is to import the necessary libraries. First of all, we need the NumPy library. Then, from SciPy.stats, we will import binomial distribution. Binomial distribution is denoted like this. Now, let us verify the binomial distribution for a single experiment. Let's define n1, that is our value for n is equal to 1, the probability value of 0.5, and let us assume that k1 is equal to 1. Let us provide a statistical interpretation of these parameters. N1 is equal to 1 means that we are tossing a coin only once. P1 is equal to 0.5 means that we are tossing a fair coin, and K1 is equal to 1 means that we are looking into the probability of obtaining the head. The probability of obtaining a head in a single experiment is computed like this. We type binomial, then we type PMF. PMF stands for the probability mass function. The first input of this function is k. In our case, it's k1. The second input of this function is n. In our case, it's n1. And the third input of this function is the probability p. p1 in our case. Okay, so let's evaluate this expression and let's see the result. And obviously the result is 0.5. And this is as expected, since we expect that we have 50% of chance of obtaining a head in a single toss of a coin. Next, let's solve the problem of computing the probability of obtaining 3 heads in 10 trials of tossing a fair coin. Again, N2 is equal to 10, since we have 10 trials in a single experiment. Then, we are tossing a fair coin, P2 is equal to 0.5, and K2 is equal to 3. Since we are looking into 3 heads in 10 trials, let's compute the probability. Again, we type binomial dot PMF and we specify the parameters K2, N2, P2. And let's see the probability. Wow, here's the probability. It's around 12%. It's very unlikely that we will obtain 3 heads in 10 consecutive tosses of a coin. The chance is only 12%, as you can see over here. In these two examples, we computed the values of the probability mass function of the binomial distribution for a specific and fixed value of k. However, we can compute the values of the probability mass function for many different values of k. Let's learn how to do that. Let's select N3 as 20 and P3 as, for example, 0.5. And let's create an array of k values. K values is equal to numpy.arange, and we need to specify the number over here. The number should be N3 plus 1. Let's see the vector of k values. Here it is, from 0 to 20. Perfect. Next, let's create an array of probabilities or PMF values for given k values. To do that, we will type the following. PMF values is equal to binomial.pmf, and over here again, instead of specifying a single value of k, we will specify the array. We specify N3 and we specify P3. Let us evaluate this code line and let's look into the PMF values. Here they are. Perfect. How can we verify that these PMF values are correctly computed? Well, PMF values are actually probabilities. And if we sum all the probabilities, we should obtain 1. So let's do that. And let's see the output. And it's correct, so the sum is equal to 1. Next, let's learn how to generate a plot of the binomial distribution's PMF. Here's a piece of code that I've wrote that will generate the plot. Over here, I set the figure size, then I plot the k values and the PMF values, and I plot them as blue circles. I set the circle size. Then over here, I draw vertical lines from the x-axis until the PMF values. I set the title, I set the X label, Y label, I adjust the font size on the X and Y axis, I set the grid, I save the figure, and finally I show the graph. So let's see the graph. Here it is. It looks perfect. On the x-axis we have k values, and on the y-axis we have PMF values. Next, let's learn how to compute the percentiles of the binomial distribution. Piece of cake. We just need to type binom, then we need to specify ppf as a function. We specify the percentile. For example, if we want 5 percentile, we will put here 0.05. We specify n value, we specify p value, and let's see the output. Okay, it's number 6. So when k is equal to 6, we obtain 5th percentile. Okay, let's verify the percentile corresponding to 50th percent. Consequently, over here we will type 0.5, and the result should be obviously 10. Perfect. Next, let's learn how to compute the first 4 moments. We compute the moments like this. I will specify the returned results, so the mean value, variance, skew, and the third one, Kurt value, is equal to. We type binom, we call the stats, we specify n3, p3, that is the n and p values, and we specify this keyword moments equal to mvsk. Okay, let's see the result. Here's the mean, here's the variance, and that's it.